But anybody have any questions? We were doing laser and electron beam yesterday and comparing the differences. Turns out, actually, there's also, I got a couple hand around things. These I didn't have time at the end of the day to hand around. This is a pulse from a 5 kilowatt Hitachi laser from 15 years ago. There's actually two. It's a piece of lucite or plexiglass, polymethyl methacrylate if you happen to be a polymer person. It turns out the beam is generated in a circular annular tube, or a circular tube of gas, and this is what's called a fast axial flow because you got to cool the gas, so you just pump it down the pipe. And as a result, you get what we call, and I'll talk about it in a little bit, multimode effects. You actually get diffraction spots. So if you feel the surface, actually you can see it, but you can also feel the spots on the surface. This thing is kind of bubbly, or has kind of little bumps on the surface. And those are diffraction spots from the multimode of the laser. You basically have interfering, you have different wavelengths across here, or not different wavelengths, all the same wavelength. But, well, I might as well explain it. Multimode laser, if I have a half wavelength this way and a half wavelength this way, it's basically a Gaussian heat source, and that's a transverse electronic mode 00. Okay, where I basically have a half wave in this direction, a half wave in this direction. If I had a full sine wave this way and a full sine wave this way, if I looked at my intensity where the sine waves add, you'll get higher intensity, and when you get where the sine waves are subtracting, you'll get, one's plus and one's minus. They're interfering, you'll get a lower intensity, and so you'll get a speckled pattern when you get to multi-mode. So you could actually probably count across here and see how many wavelengths of the diffraction interference pattern you have across here. So now the other one is a deeper one. You can look sideways and you can see how deep it is. All they did was essentially, if you take a circle and turn it on its side, its projection becomes an ellipse, right? If you do that and you turn it a lot on its side, now the projection is, you basically turn that ellipse into basically a line heat source. And so that's what they did here. It's all done with mirrors when you work with lasers. So there's an ellipse on the surface, and they got greater power density, so it dug a deeper hole when you just turn the beam. These other two are basically just samples that they were using at Edison Welding Institute to check out their laser. Pretty sure I got these from Edison. And they're just little blocks of the same type of lucite, and you can look and you can see the non-regularities. If the beam is not symmetric and whatnot, you'll see a little peak in the center, or actually it's a dip in the center. You're looking at the negative image. Pardon me? Oh, for those things, actually a lot of times they actually pulse it to do that, to get a deeper impression. But it depends on the power of the laser, but you might do 10/10 of a second pulses, so it's like a 1 second. When you're going really deep like that, you actually kind of tend to pulse it rather than just try to, otherwise things all start melting and heating up and stuff. But if you pulse with the same power, you'll get the impression the first time, but you magnify it as you keep on pulsing the same thing over and over. And you can see how uniform your beam is. Now, your beam is, depending on the power of your laser, a 5 kilowatt laser might have an axial flow of inch and a half, 2 inches in diameter, depending on how it's designed. And you've got to focus that down to a spot, which is you do with curved mirrors. Now, one of the problems with the mirrors is you'd like to use copper because it makes a very good mirror. It's a good reflector, right? And they do use copper to machine the mirror, but they tend to gold plate them. And the reason they gold plate them is the same type of thing we were talking about yesterday. Copper will oxidize in the air. And copper oxide is a very good absorber of laser light because it's a ceramic. It doesn't have free electrons. So if you were to use copper mirrors, straight copper mirrors, yeah, the copper will carry the heat away. But if you get a little bit of copper oxide and you hit it with the high power of the laser, you actually pit the laser and melt right there where those little black spots of copper oxide are. So they tend to gold plate it because gold won't oxidize. So they tend to use gold-plated copper mirrors in this stuff. But it's really just because of the oxidation. You also have to keep them clean. You get a speck of dust on there, and now the power comes in there, and it, you know, it heats up the dust and hits the mirror there too. So there are a number of headaches with using high power lasers. Although nowadays they can get to YAG lasers. You can't use a CO2 laser with fiber optics because it's 10.6 micron radiation, and there are no fibers except diamond, and diamond fibers are not cheap. Actually, they don't exist in the lengths we need. But diamond will transmit light all the way down to about 50 micron, or as long as 50 micron wavelength. But most materials will not transmit light much below a couple of microns, or longer than a couple of microns. So you have to use a YAG laser at 1.06 microns. If you use a good quartz fiber, you can use fiber optics to transport the beam, that's nice because you don't have to have mirrors and tubes and stuff to protect the area where you're going from the laser generator to the workpiece you want to do whatever you're going to do with. In recent years being the last 5 or 10, we now have YAG lasers that go to about 2 kilowatts, and we have fiber optics that don't melt when you put 2 kilowatts through them. So now you can basically just have a flexible cable that'll carry the laser beam right to where you want. It's not particularly cheap, but we can do it. And that actually was a big, I think Sandia National Labs led the charge on trying to develop that because they like lasers for putting together nuclear weapons. Okay, so that's kind of the theme from yesterday, and we're going to continue on that theme. I think we're up to 8 right now. Electron beams are distorted by magnetic fields, and lasers, photons, are not affected by earthly fields. What fields are photons affected by? Big gravitational fields. Look at Scientific American this month. They have an article on magnetic lenses, electromagnetic lenses, and bending of light as you go across as light goes past some galaxy or something. Not usually a problem in welding. Okay? But there's a nice computer simulation of how the logo of Scientific American gets distorted in space. Okay, so far as electron beams being distorted by magnetic fields, it can be a problem because a lot of what we weld could be heavy steel things, and steel can pick up ferromagnetism just from the Earth's magnetic field. Steel can be magnetized. And so it turns out one of the things people do to avoid the field problem is outside or in the vacuum chamber from where it comes out of the electron beam chamber and the magnetic focusing coils, you just put a steel tube around it. And it turns out the steel tube is sufficient to shield the magnetic fields, and so the beam goes straight through the tube. If you took the tube away and you had a magnetic field, the beam might just turn a couple of inches and completely miss your weld joint. So you could have a standoff distance of 1.5 feet in some heavy section electron beam welding machine, and if you didn't have that tube there, you could miss your joint by a couple of feet just because of the residual magnetism in the steel. Simple solution: just put a steel tube to surround the path of the beam that you're interested in controlling. So far as the size of chambers for electron beam welding, the largest one in this country was built back in the 60s by Northrop Grumman down on Long Island for titanium welding the box sections of some, I can't remember which F series it was, F-15 or F-14, might have been the F-15. But it's big. In order to hold the wings on, which one has the swept wings, the wings that can move back and forth? 14? Okay, the 14, and so is the F-14. And they have this big box section with these hinges so the wings can move forward and back. And in order to do that, originally they were going to build a huge forge. That was the one I told you about. They were going to use a mountain in Colorado for the foundation. for the forge if you were in 3371. But instead of doing that, they learned they could build an electron beam welder and make these heavy titanium sections. And so it's a chamber that's almost the size of this room, so far as that goes. The world's largest chamber, at least as of 10 years ago, unless someone else has built one, is about twice the size or 3 times the size of this room, and Mitsubishi Heavy Industries owns it. And they basically made it for some reason, I think for some nuclear energy experiment or something. They were building a bunch of big stainless steel pressure vessels, like 2 inches thick. And they were building enough of these, it turns out it was either economical or they got some help from the government to prove out the technology, and they built a big chamber. So you can get some pretty decent sized chambers. So far as being distorted by the magnetic fields, if you try to weld dissimilar materials, if I have electron beam weld on a piece of carbon steel and a piece of alloy steel, like chrome moly steel for a steam generator plant or something, I can weld them, but the problem is if it's very thick and I put the beam will go in there into the joint, and if let's say the joint's 4 inches thick, if the joint's 4 inches thick and I have dissimilar material, the beam may come in straight and it may bend to one side within the material. It may take a couple of inches to do this, but what's happening is I heat up the material. I have what's called the Seebeck effect. The Seebeck effect is the same principle as the thermocouple. If I have a temperature difference in two materials, 2 different metals, like copper constantan or chromel alumel or platinum rhodium thermocouples, I will actually generate a voltage because of the temperature difference. And that voltage will drive a current. So if I'm welding 2 different steels in a very heavy section, people find that it's impossible to keep the beam straight because you actually generate a voltage within the material, set up currents which set up magnetic fields which bends the beam. There is no known solution to that. Okay? So they tend not to use it. Another problem, or a problem with electron beam, is it produces X-rays. And over here, whoops, that's 8, this is 9. We have intense light. Which is typically invisible in the infrared. Even a YAG laser beam is invisible to your eyes and my eyes. It's 1.06 microns. We only see out to about 0.7 microns. Okay, 700 nanometers or 7,000 angstroms, right? In terms of wavelength. One of the problems with lasers is that the reason they don't want you looking at them is if this is your eye focuses the beam as it comes in. That's what your eye is supposed to do. And it focuses the laser light, so even if you have a relatively low power beam coming in, and it wouldn't hurt your skin, it will burn your retina because you're basically intensifying it because your eye is a lens. And so that's why lasers are dangerous to your eyes. And you have to be careful. Typically, I mentioned yesterday, they put the lasers inside a big plexiglass enclosure. You can see plexiglass will stop the beam if it's just a reflected beam. Because otherwise, you've got people walking around and they wouldn't even see it, but they could get flashed in the eye and blind them. Okay? People should be wearing goggles, to protect themselves from the light. So far as producing the X-rays, because it produces X-rays, there are typically electron beam chambers of less than 40 kilovolts or greater than 100 kilovolts. And we tend not to see, I'm not saying, I have heard the French built one at 60 kilovolts, but only the French would do something that stupid. I don't care much for the French, even though I'm about a quarter French or almost a quarter French. The French are just arrogant, that's all. That's the problem. In any case, the below 40 kilovolts, you produce X-rays, but the X-rays can be, those types of X-rays can be stopped by any type of vacuum chamber. Just a regular glass window in a vacuum chamber will stop 40 kilovolt X-rays, and so the vacuum chamber itself is the X-ray protection. You start getting above 40 kilovolts, and now the X-ray intensity is getting to the range where you need to have much better protection than just a sheet of stainless steel or a glass window or whatever on the chamber. And in fact, in 100 kilovolt X-ray machines or greater, they'll have leaded glass that might be 2 inches thick, because you've got to stop the X-rays from irradiating all the people around. So it turns out there's sort of a never land, unless you're in France, between 40 and 100 kilovolts. It doesn't really cost you more to make a higher voltage beam. I mean, it's just how many turns on the transformer. The transformer is pretty much the same cost, so far as that goes. So if you're either going to try to keep the power below 40 kilovolts, or the voltage below 40 kilovolts, or if you decide that you're going to pay for the extra insulation or shielding on your chamber, then you'll go ahead and go up to 100 kilovolts. And why is that? Because here the beam current is limited to half an amp approximately by mutual repulsion. Is that how it's going, Rachel? Of the electrons. If I have a beam current of 1 amp, an electron beam, it turns out the electrons will be close enough together they will actually defocus. You can put them in a magnetic field and squeeze them together to focus them, but as soon as they get out of that field, they have enough repulsion, they will actually defocus. If I'm building an electron beam melting chamber, I can go to 3 amps, 10 amps, whatever I want, because I don't care. I'm not looking for a fine spot size. I can have a spot size, 10 inches in diameter in a great big electron beam melter. And I don't care about mutual repulsion of the electrons in the beam. But for a welding machine, I want a focused beam, and that means if I go to a current greater than about a half an amp, the beam starts to defocus. In fact, in most cases, you rarely see beams much more than about a tenth of an amp. However, if I got a tenth of an amp and 40 kilovolts, that means I got a 4 kilowatt machine. That's the maximum power I could get. Or if I have a half an amp and 40, I'd have a 20 kilowatt machine. 20 kilowatts would be fine if I'm going up to 3/4 of an inch, but if I'm trying to get greater thicknesses in electron beams, I can't do it. I can't electron beam weld. I can't make a 50 kilowatt machine with 40 kilovolts or even 50 kilovolts. I'm going to have to go to 100 kilovolts to make a 50 kilowatt machine. So if I want to weld 2-inch or 4-inch thick material, I typically might go to a 200 kilovolt half amp machine. Okay, and there are 100 kilowatt machines out there. The Japanese actually built a 600 kilowatt machine for research purposes, and because the Japanese just like to do things that are bigger than anyone else to say that we have the biggest one in the world, right? It's kind of a national pride thing. Okay, over here, no interaction of photons. So there's not a problem of defocusing of the beam or a limitation of the current. A beam is easy to manipulate. With magnetic fields. And here we have what I already talked about, the problem of diffraction spots. So the beam is distorted by diffraction spots or non-uniformities of the flow in the gas generator of the laser due to differences in density of the gas due to temperature differences within the tube where you're generating the laser light. And you have these different TEM modes for diffraction spots, okay? And they can get very complex. The best welding occurs in the TEM00 mode. The problem with the TEM00 mode is a axial flow laser, like that Hitachi laser, that can put out 5 kilowatts in the multi-mode, where you have lots of different diffraction spots, can only put out about 2 kilowatts in the Gaussian mode, just because it has to do with turbulence in the gas and non-uniformities and densities of the gas as it heats up. So far as manipulating this with the magnetic fields, typically on a laser beam welder or a laser surface hardening apparatus, you can just apply an XY field and you can scan the thing wherever you want. In fact, I had a student once doing studying electron beam welding of stainless steels, and the laser they had out at Lawrence Livermore, where he's working, basically could sweep at 1,000 inches a minute. They just had a magnetic field. I mean, the beam came straight down, but the magnetic field just deflected it. There's 1,000 inches a minute. It might have been 1,000 inches a second, but he went to tremendous speeds. I mean, he went over a range of speeds, but he went to tremendous speeds with the electron beam because you just turn on the magnetic field and sweep the thing across. Now, if you're trying to do laser hardening of a surface, not laser hardening, but electron beam hardening, you typically may apply these fields and have a sine wave in this direction and a slightly different sine wave in that direction. And so instead of the thing just going around in a circle, it makes a pattern kind of weaving around. Anybody know what that pattern's called? Any of you electrical engineers? It's a Lissajous pattern. After the name of the guy who originally developed it or whatever, but a simple Lissajous pattern, if I have two different frequencies of sine waves, will form something that kind of looks like that, but a complex one, you end up getting all these fancy patterns if you have two different frequency sine waves, one driving X and one driving Y. You'll get the thing take all kinds of things, but it will time average out, so you get the whole square or rectangular area. And you can do these Lissajous patterns on an oscilloscope. You just have two signal generators and you change the frequency and you go to an XY mode on your oscilloscope rather than XT. Instead of time, you just go XY, you put in a different module. And you can draw out these Lissajous patterns. Okay, you can become an artist. You can get all kinds of weird patterns. If you just spin the knob and change the frequency, it's sort of neat. Yeah. Transverse electronic mode, okay, if you're really interested. I'm pretty sure it is. Either that or it may be Dutch or Belgian or something. I don't know. Okay? You trying to defend the French? Okay. Huh? No one ever told me I didn't have opinions. In fact, I usually have an opinion on most things. Did anybody read the tech talk about what Noam Chomsky said about Afghanistan? Sort of humorous, wasn't it? I mean, the logic. I mean, here's one of the brightest men at MIT, right? And I was here during the Vietnam War, and he was I don't know if he's an institute professor back then, but I mean, he invented the field of linguistics. And now he's an institute professor or something, but the fallacy of his logic, is just incredible. It's a good thing some of these people are good scientists, because they certainly aren't very smart otherwise. He basically said, we're committing genocide in Afghanistan because there's 7 or 8 million Afghanis who are starving. I want to know how many were starving before September 11th. Okay, he didn't kind of talk about that. He said, we're the terrorists. And we're terrorizing the world, and the only way to stop terrorism is to quit perpetrating it. Well, that's exactly what Chamberlain did with Hitler in the Sudetenland, right? Appeasement's been around for years, right? I mean, he claims that we're the ones committing genocide on the Afghanis, but we're not the ones who have said that we want to kill every American in the world, right? We haven't said we want to kill every Afghani. I mean, You know, his logic just is incredible. But the way to defeat someone in a debate like that, you have to recognize everything they're accusing you of is exactly what they're doing. I mean, I've learned, it took me 20 years to learn this, but typically when you have zealots like that, they will, whatever they accuse you of is exactly what they're doing. And that's their whole approach, is that they go on the offensive by telling you that you're doing what in fact they're doing, okay? And so all you have to do is kind of recognize that's what they're doing, and you just reflect back and point out that, no, it's not me, it's you that's doing that, okay? But if you read the tech, the person who wrote the article for the tech was very impressed with his arguments, okay? Yeah. Yeah, it's, what do you call it? It's a, I always forget the name. It's not a charlatan, it's a demagogue. A demagogue is someone who panders to people by telling them what they want to hear, okay? Now, I have no doubt that Chomsky believes everything he says. Anyway, I was going to tell you the sample heats uniformly. The only problem is that just because he believes it doesn't make it true. Okay, I mean, I actually believe Osama bin Laden is one of the most honest, sincere people in the world. He believes very strongly in what he believes. You may not agree with what he believes, but he's not afraid to state it. Oh, that was another thing he said, is we have no proof that Osama bin Laden did this. Well, Osama bin Laden has admitted it on TV. I mean, so what proof do I need? You know? Gee. You know, so in a debate like that, well, that's the question you ask. Well, what proof, what better proof than personal confession would you like? Okay, what standard are you trying to uphold here, right? Anyway, it turns out in the lasers, inclusions in metal heat preferentially. And why is that important? Well, it turns out the Navy found at the Naval Research Lab when they were using high-power lasers to weld HY80, they actually got better properties in the weld metal than they did in the base metal, because it turns out you end up refining the metal. When the laser hits the metal and you've got these little ceramic particles, well, the ceramic particles absorb the laser light better than the steel does. And so you vaporize out the inclusions, the dirt in the steel, and you end up getting better properties. Now, you can now think about other things. I got a call 10 or 12 years, 15 years ago, whatever it was, from someone from a company that wanted to make, or that was trying to sell aluminum silicon carbide composites. So you have these little silicon carbide composites in aluminum. And they said, we'd like to give you a research grant to laser weld this material. I said, no way, it's not laser weldable. They said, why not? You've never tried it. We just made this material. I said, yeah, but I know it's not laser weldable because you got a ceramic surrounded by a very reflective material. I'm going to preferentially heat the silicon carbide and decompose part of it. It's going to form aluminum 4 carbide, which is attacked by water. And so you're going to end up with basically a product that would stress corrosion crack, but you're also going to end up with a lousy joint because you're going to superheat the silicon carbide and you're going to reflect from the aluminum. You're going to end up with a terrible weld. Well, we'd like to give you the money anyway. I said, well, I'm not going to accept it. I said, why don't you go to Ohio State? They'll take it. And they did. They went to Ohio State. They took the project. A student who used to be a technician in the Navy down at David Taylor had applied to MIT, but he didn't get in. He went to Ohio State, and he got the project. And so what does he do? I told him this story when I was down at David Taylor. So he calls me up to ask for advice on how to do it, because his advisor didn't have any idea on how to do it. So I told him, you can't do it. So he did his thesis on it, and he proved it can't be done. So what can you say? Okay, that's it. We ought to hand out these little things.